Hello, and welcome to today's webinar, How to Build Rotary Indexing Tables for Specific Applications, brought to you by Design World Magazine and Nexen Group Incorporated. Again, I'm Lisa Eitel, Engineer Editor with Design World Magazine. Before we begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply ask for help through the question box on your GoToWebinar console. Get social and share information from today's session. Tweet or post on this webinar and hashtag your post to join the conversation with hashtag DWWebinar. We welcome your questions today at any time, particularly those that relate to indexer components. Just enter questions as they occur to you in the question window on the side of your GoToWebinar console, and we'll answer as many questions as possible during the Q&A session that will follow the main presentation. But again, just feel free to type in your questions at any time. Just a quick bit about me. Again, I'm Lisa Eitel, Senior Editor at Design World with a Bachelor of Science degree in Mechanical Engineering from Penn College, now Washkowitz College at Cleveland State. I've been a technical writer for 14 years and was the Chief Editor of Motion System Design. Today I cover motors, drives, motion control, and mechanical power transmission for Design World, and I serve as a judge for local FIRST robotics competitions. Our speaker from Nexen Group Incorporated is David R. Bickert, with more than 24 years of work experience in automation and motion control. Bickert has a Bachelor of Science degree in Mechanical Engineering Technology from Penn State University. His graduate degree is an MBA from Fontbonne University in St. Louis, Missouri. He has a range of experience as an application and project engineer, as well as a manager in engineering, marketing, and sales positions. Bickert currently holds the position of Regional Sales Manager for Nexen Group, where he's worked for more than 13 years. This is just a tell you what I'm going to tell you slide. Essentially, in this webinar, I'm going to give you a brief overview of mechanical options for rotary indexers, and then servo drive options, and some direct options, and then detail some applications. Next, I'll turn the floor over to David Bickert so that he'll give you specifics on how to pick a rotary indexer from concrete specifications. We have some example setups on this slide from DSTACO and ESUM Automation. Thank you very much. So let's just cover the basics of rotary indexing systems first. So manufacturing processes need short and repetitive moves around a rotary platform, as we see here. For example, assembly, machining, as well as bottle rinsing and filling and capping in food and beverage, all make use of these rotary indexers. Usually they're taking arrays of relatively small parts around a turret through stations to process discrete parts on product assemblies. Rotary setups that incorporate electric motors dominate. These take the form of either cam drives or servo tables. The traditional option here for rotary indexers is mechanical cam indexers. Engineers have actuated rotary indexing tables with these for years. They're low cost and limited by the way they always index to the same angle, unfortunately. However, their real strength is their precision moves. Most mechanical cam indexers use one of 3 mechanical cam types to move loads into position. The cam's curved surface engages a follower for repeatable motion. Shown here is a really beautiful example from Cavalry Automation. Oops. We might go back there. Cavalry Automation is based near Rochester, New York. This is a high-tech integrator that sells synchronous and high-speed assembly platforms with integrated cam motion, pick-in-place, or probe units, mostly up a common drive shaft. The particular offering from Cavalry uses rotary indexer subsystems from companies including Camco, Stelron, Cam Driven Systems, and Sankyo. All right, so this is a good slide to stay on for a moment here. Some cam indexers work by cycles on demand, as you can see here. The camshaft turns once to advance the output 1 position, essentially. A camshaft sensor tracks position, so controls tell a drive when and how to run that motor. A long camshaft dwell from, say, 1 second to hours, literally, let the shaft stop over time without degrading positioning accuracy. Here we have an example from Cam Driven Systems, just mentioned on the previous slide. There is one catch. cycle on-demand rotary indexers must accelerate the camshaft during dwells before output motion starts. The need for acceleration limits how fast these setups can output motion. Cycle on-demand rotary indexers must also accelerate the camshaft during dwells before the output motion begins. Check out the illustration on the right from Nguyen Duc Dang of a similar setup using a belt drive downstream. You can find this and automation illustrations on YouTube. Just search THANG, an indexing table, to find more. This particular individual has got some really nice illustrations kind of catted up in Autodesk Inventor, and these illustrate several different indexer options. The machine shown here has bevel gearing and a drive to move the table, I think illustrated here in orange, up and down. Next slide, please. We're just going to go one back. We have examples here from Neugard, USA. Yes, perfect, thank you. This is planetary gearing in the upper left. The bottom example is a Fibro brand indexing table with planetary gearing specifically for side machining applications. At the opposite end of the spectrum, gear choice-wise, some indexing tables make use of worm gearing. So the example here, center top, is from Cone Drive. Cone Drive supplies some components specifically for indexing machinery built by Celeron Incorporated out of New Jersey. All right, next slide. Thank you. Other mechanical cam indexers run continuously, so the motor always drives the camshaft. The cam profile basically dictates dwell time, which is helpful where other machine tasks are really fast or synchronized with the camshaft. These continuous indexers run 800 cycles a minute or even faster. The only catch here is that mechanical cams needing long dwells and fast indexing may be hard or even impossible to physically build. So here we have a really great example from Motion Index Drives in Michigan. This is a barrel cam. You see it on the right there. The application example on the left is Bosch Packaging design. It's a pen assembly machine. This rotary assembly machine, it's called an MRA. It puts together disposable medical pens such as single-use auto-injecting insulin shots. Next slide. So consider this other example on the left from SSH Automation based in Singapore. Hopefully the animation will come through a little bit. SSH is online at shautomation.com.sg, and the company sells cam indexing components that include globoidal and barrel cam subsystems, which we'll describe more in a moment. You also see here pre-integrated drives specifically designed for indexing applications. These are, if you need to know, HA, HD, and HP drives from SSH, and in fact, most of the company's drives use roller gear mechanisms. Next slide. Thank you. Here are some QR links if you happen to have your phone handy to get directly to some animations. I'm not embedding them here. I just want to avoid some display issues, but essentially we have rotary indexing permutation in the form of the barrel cam. That's on the bottom there. The real world photo of a design using the barrel cam is the Weiss TH series rotary barrel indexer. Weiss is a great company. I happen to know them personally. They're pretty close to Design World here in Cleveland, Ohio. Really nice people. On the top of this slide, we have a screenshot of that globoidal cam animation from CDS, Cam Driven Systems. Also very nice people. If you're curious, want to get a little bit more from them, I edited a pair of articles years ago about cam-driven machinery with Robert Zaruba there. So you can Google Z-A-R-U-B-A to find those articles. Next slide. Thank you, Stacy. There's another option for rotary indexing, though. Besides setups with mechanical cams, indexers can also use programmable servo drives. These are really helpful where applications need flexible motion output that's not necessarily always needing to come to the same exact station positions. So case in point, a machine may process multiple products needing different positions. Other examples where servo tables really excel are those needing fast positioning and long dwells. So rotary indexers running off servo control output moves essentially when the servo motor starts moving. Some rotary indexers use servo setups using gearing, such as the preloaded gear reducer shown here. The red colored CAD drawing is another example in the upper left there from CDS. What you see here with the 3 insets is a roller drive from a company called Sankyo. They have U.S. facilities here in Sydney, Ohio. The zero backlash nature of the reducer minimizes settling for accurate positioning, and it makes for better response. The third image you see is actually an tall plant indexer to place parts for assembly. Next slide. Thank you. So in contrast, some other options we see on this slide are direct drive servo motors from Cole Morgan in the lower right-hand corner here. Back in May, Design World published a fantastic piece, highly recommend you check it out, by Hurley Gill, very knowledgeable guy from Cole Morgan, where the 2 drive options shown here, as well as the indexing application, is explained in detail. In the article, Gill essentially explains how inertia mismatch is not a concrete number, and there's not even a concrete range for every application, but there are some ratio ranges that are applicable and acceptable to specific applications. So the article goes on to kind of explain how super dynamic indexing sometimes benefits from a higher than you might expect inertia ratio, something like 8:1, for example. So check it out. Next slide. All right, here's a specific example of another direct drive option. It is a direct drive servo motor from IntelliDrives. The thin rotary table is a model ACR55UT, if you want to check it out. It's got a 55mm center aperture for applications in semiconductor manufacturing and other similar precision applications. So it runs from 1/10 of a rotation per minute to 1,000 RPM with velocity ripple of less than 0.1%. A high torque to inertia ratio makes for quick stop-start cycles, and that makes for short settling times. That makes this setup essentially outperform traditional direct drives and drivetrains incorporating gears. Next slide. And some manufacturers offer both traditional motion setups and direct drive options for indexing. Check out these from one of our other favorites, a company called Bell Everman. Mike Everman is the founder, fantastic guy and kind of just a inventor. Baker will expand on the strengths and weaknesses I've mentioned here just in a bit. So next slide. Thank you. All right, so the real point here is that selecting programmable indexing tables is easy, but the dynamics tuning and optimization for efficiency are non-trivial. This is the complicated stuff. In short, mechanical cams for indexing are fast and deliver high repeatability and torque. They can run for millions of cycles, even for very high inertia systems. They also move large loads more quickly than certain electronic setups. But setups with direct drives and electronic camming excel where applications need lower inertia or have lower inertia and they need variable output. Electronic camming with traditional servo or even direct drive setups can have lower inertia, so they work with light or moderately heavy loads. They use servo motors, drives, and controls, and feedback devices. So all of those components cost money. It's something to keep in mind. But systems with electronic camming excel anywhere applications need flexibility. So with all this, it begs the question, for a given index or application, how should engineers plow through application such as indexing angles and speed and required dwells and the moment of inertia to pick the most suitable? Also, what about the table design itself and its orientation? So we have motion components and system manufacturer on the line. Next slide. This is where I'm going to turn things over to David R. Bickert with Nexen Group. Again, Nexen Group sells linear and rotary components for motion applications. So David will outline calculations involving mass, inertia, index time, accuracy, and repeatability to get the right indexer for a given application. He's going to detail for you how to apply rotary motion products in a design, as well as some critical elements to consider, from the motor and gearing, where applicable, to the drive and controls, all the way out to the dial plate. Then he'll give you a demonstration on the variables that can affect performance and product life. So David, the floor is yours.
Okay, thank you, Lisa. I appreciate the overview and the great technologies that you just went over for rotary indexing. Appreciate being here today to discuss rotary indexing. And I'd like to begin by illustrating just a nice machine cell graphic from Icon Industries. One of the reasons for this is you can see that at the heart of the machine cell is a rotary indexer. And what we are talking about is the cell has a number of workstations surrounding a rotary index table, and the rotary index table is really the center of the processes. And this is where you can see that surrounding it there is a robot and there are some CNC activity, but you can have a number of different stations with a lot of resources surrounding the indexer. And in this case, the indexer has a table on top of it, and it is actually shielded in the work cell. So I wanted to start with that as an example and then get back to what we were previously discussing. And Lisa indicated that there are some different technologies, one of them being a belt drive, cams, direct drive motor as well. So oftentimes we can see that a belt drive can be quiet, it can run at high speeds, but there is the possibility that you can have some belt stretch, a lot of times accuracy compensated through electronic feedback sensors, programmable typical items that are needed at that point. A cam mechanism is certainly a proven technology. You have the fixed index globoidal cam design, and it incorporates its own motion profile for displacement. There is an oil reservoir, and it's used for lubrication. Sometimes that has limitations on the mounting orientation. And of course, direct drive motors eliminate mechanical transmission components, so you get zero backlash. Sometimes the load capacity can be limited. And so one of the technologies for gearing that I'd like to start to discuss is the roller pinion technology. And roller pinion gear technology combines a lot of features, both mechanical as well as programmable. It is 99% efficient as far as the mechanical roller gear transmission system. It's rigid. It's a rigid gear system allowing for low maintenance, high torque capacity. It's also very flexible, where you have the ability to do programming for the various displacements that you're looking for. So if we look at a graphical depiction, this would be typical, where you would see that with the servo motor on the right, you have a pinion, and the pinion is attached to the shaft of the servo motor, and it's going to combine with the gear inside of the housing. And this is nice because it is low maintenance. It's a sealed housing. The mechanical gearing for a wide range of different product applications. And you have the pinion, which is the roller pinion technology feature, and I'll get into that a little bit here on the next slide. The RPS technology is unique. You can see from the cutaway that we have two or more low coefficient of friction, low inertia rollers that are always engaged via a preloaded system. So the the actual rollers themselves are in opposition. And when the rollers actually are in opposition to each other, when they are engaged with the gear, you actually are eliminating backlash. So you're eliminating cumulative error, and you have quiet and smooth motion. Now the gear diameters can be changed for ultimate capacity and design functionality, and the pinion being preloaded into the unique gear basically gives you some options. If we look at that a little bit closer, we'll see that the roller pinion system, the rollers actually create the curve, and you have theoretical teeth from the rollers. And with that, the result is a durable, flexible, mechanical system, and it actually has very high accuracy as a result. So using this technology, what we're able to do is we're able to look at a packaged roller pinion technology system for rotary indexing. So this slide gives you a good example of what we're able to do. We have a programmable index displacement, flexible mounting, low backlash, of course. The slide captures one of the 1.5 meter bolt circle diameter units, the PRD 1500, which is capable of plus or minus 11 arc seconds for accuracy. The repeatability is 1.2 plus or minus 1.2 arc seconds. The output is a cross roller bearing, and it provides for high load capacity. Also allows for various orientations. It's beneficial whenever you have external forces applied. So this packaged indexer, it's shielded. Some of them are rated for IP65. There is no oil reservoir that you need to worry about. And a very nice benefit is the large center opening and the rigid steel base plate. The base plate is important because of the rigidity. So if we look at a typical indexing, what are we talking about? We're usually looking at a dial plate. And so you can see that I have on the slide the external dial plate indicated with the arrow. And if we look over to the graphic on the left, you'll see various stations. This is a 12-station dial plate indexing. You can see that the dial plate, which is the rotary option on top, is going to be indexing. And in this case, it'll be 12 stations. Over we can see that we are looking at a visual with regard to force in the axial position, force in the radial position, torque at the output, and moment torque. These are all parameters that need to be considered when you're looking at a typical indexing application. It's important to consider force applied. The forces can be singular, they can be a combination of axial and radial force. The total output torque and any moment load that there may be has to be considered. And so if we get into the bearing construction, that is always a consideration when looking at applying anything that is going to be axial load or moment load. So in this diagram, if we look at the left, we'll see that the axial load, in this case, we have the customer machine frame, which is parallel to the floor. The dial plate, of course, being on top where the load is. So you can see in the illustration the axial load on the left, which the load is indicated in kilograms. And over at the right, you can see that this load in kilograms is moved over to the edge of the dial plate. Now, if you don't have a balancing situation opposite that, you will see that there is a moment load that needs to be considered, because now you have a load out at the edge and it is balanced. So the bearing construction is always a very critical part of any indexer application. If we look at the external force considerations, here on the left, you can see that the spindle from a drill in a CNC machining application, you'll have an axial force being applied downward to the actual product. Over to the right, you can see the same thing from a setup, and you can actually see the illustration where there would be the gear and the pinion. It's important that the indexer and the bearing are very, very accurate. Accuracy and repeatability capabilities always come into consideration in addition to the external forces that are going to be applied. I talked previously about the fact that some units require oil, and this is also an important area whenever you're looking into your design, because you could have a situation where you have an upside down orientation. The robot in the center is actually hanging from above, so you might say that it's hanging from the ceiling. In this upside down orientation, you need to be looking at the upper support, but the suspended load must be considered, as well as any oil that could be in the system or any type of seals that are holding that oil. So in many cases, if you have a device that is going to have an oil reservoir, it is not recommended that it be used in an upside down vertical position. If you have a system like the roller pinion technology, it is a gear and it does not require an oil reservoir, and it can be oriented in any position. So it's an important factor to consider. Over to the right, we actually have another orientation, which I call perpendicular to the floor. And you can see over to the right that you have an illustration showing the radial load, which is the distance from the machine frame to the radial load must be taken into consideration. So a lot of times you want to look at how thick is the housing of the unit. Is it compact? Where is the bearing structure? And where is the load being applied? In a perpendicular orientation, it's very common for what they would describe as a headstock application. And here, in a typical headstock application, it's an automated welding. The indexers can be used in the headstock or the tailstock. So in this illustration, it would be either at the left or the right, or the combination of two, using electronic time to put it together. The bearing consideration is flexible, and the mounting orientation and access through the output center are very important factors. You can see that from a headstock, tailstock application illustrated that the center opening is important to bring wires through the opening. You can actually use a rotary indexer to the right in the orientation for the robot as well, which would be more like your typical dowel plate indexing application that we discussed previously. So it's a combination of the two. So why do you need an opening through the center of a rotary indexer? That's always something that comes up as well. And these are questions that in the beginning of any design that should always be considered. So you can see from this illustration that a large through hole, I'll call it a through hole, and that's basically the hole through the output center of the indexer. This can be a deciding element, okay? When you're looking at machine cells, often large robots or pick-and-place products, they'll want to be through the center. And not to mention, you can have plumbing or access with wiring, and this is always an important aspect that you need to consider, especially if you can get a large hole through the center and still have a nice high capacity unit. So in this illustration, I like to refer to this as a stationary center post consideration. The access hole that I was just discussing previously, there's also a nice feature on many indexing products. In this case, it's the Nexen CRD product has a hole pattern for a bolt-on stationary center post. So a stationary center post is exactly that. It would be coming up through the center and does not rotate. In this illustration, you can see that the post is securing some pick-and-place devices. Now, pick-and-places are often used in conjunction with a dowel plate because you will have rotary transfer, rotary automated assembly and transfer. So it's always important consideration when you're looking at this, because if you're able to utilize a stationary center post by securing pick and place units at the top portion, then you still have a hole going through the center, and that hole through the center can still be used for the plumbing, and it can also be used for any wiring. All important features when you're looking into your indexer selection. So then we go to the subject of accuracy and repeatability. So we were looking earlier at an automated transfer and assembly with the pick and place units. And then you want to consider, how accurate do I need this to be? It's an important, accuracy basically is the rotational error or the deviation of the measured value from the true value. And repeatability can be the error between a number of successive attempts to move to that same position. So with any rotary indexing application, obviously accuracy and repeatability is going to be a concern. The convenience of a package design where you can utilize encoder feedback, as you can see in this illustration coming off of the mechanical device. You can, in this case, have a 12-station dowel plate assembly. And if we were to look at the move from station A to B, you could say that that would be a function of accuracy. How accurate is the measured value to the true value? The repeatability, that would be observed as the value of the successive moves to the same position. So when you're looking at one of those elements, whether it be A or B, and you want to look at the successive moves to that spot. Often accuracy is listed in arc seconds, and of course an arc second is 1/3600 of a degree. And that's an important conversion factor whenever you're looking at where your part and fixture is on the dowel plate and what accuracy you need. So it's important that you're getting the accuracy you need at the actual position that you need. And some mechanical devices will, they'll rely on what would be a pin design, a shot pin inserted into a hollow bushing on the dowel plate. Now, what that does is it pretty much compensates for the fact that you don't have the accuracy that you need. And a shot pin can produce a force that can adversely affect the performance of the indexer. So if you picture a pin coming up through the plate, that can put a force on the entire system. And it can also wear over time, so it's certainly not going to be the best. If you can get an indexer that has accuracy, repeatability, capability, and it's programmable, you're going to have the best of all worlds. If we look at the green rectangles on the actual dial plate here at each of the 12 stations, we'll go into a bit of a visual to give you an idea of what we have here for accuracy and repeatability. On the left, if you were to look at that, you would see that the yellow circles are somewhat random. In this case, you would have low repeatability and low accuracy. Repeatability being that it is not maintaining the same spot every single time, and the move from one position to the next is random. In the center, you have high repeatability but low accuracy. So you can see that all of the yellow circles are grouped together for high repeatability. They're hitting the same spot, but the accuracy is not good because it's not in the center of that rectangle. If we look at the right, you'll see that you have the best. You have high repeatability and high accuracy. The yellow circles are certainly in the center of the rectangle. This would be what you're after whenever you're looking at a recommendation for an indexer. If we move on to the acceleration or the motion profile of the unit, this is also an element that is very much a concern. A lot of times, since it is a programmable feature, we can look at it, and this would be the output displacement and whether it's variable for multiple applications. So can one product be recommended for several designs? In the case of a mechanical programmable indexer, you can use one part number and you can program the displacement depending on what the application needs. So the flexibility of the programmable index displacement, it's a luxury for designers who require the changeover at any given time. Here we detailed a standard ramp motion profile for acceleration and deceleration. An example is shown here for a linear movement, and you can see that the maximum velocity in this example from the triangle is going to be 2 times the average velocity, and I've given an example in linear terms at the top right. One is a motion profile, which is trapezoidal in the move. Now this is also something that is programmable, and these are just 2 examples, and you can see that in this one you have sizing where the maximum velocity is 1.5 times the average velocity. It's a good idea to always size looking at peak or maximum velocity when you're looking at your applications. And if we were to take a little deeper dive into that and look at the motion profile for a rotary example. Okay. This would actually be a rotary example where we have 18 degrees per second, and that would essentially be a 20 station dial type indexer. Now, if we were to look at this, just to put it in terms of rotary, since previously you were looking at linear, you can see that in this case, we're going to do a conversion. 2 pi radians is 360 degrees. If we look at maximum velocity, which is going to be 2 times the average velocity, as we discussed previously, we're going to get our units in radians per second. And then from there, you can look at the acceleration. And the acceleration is going to be the maximum velocity divided by the time to accelerate, and that will be in radians per second squared. So once you're able to actually determine what the acceleration is for the application, another very important element comes into play with inertia. And this is always a subject matter which basically relates back to, you could say, Newton's first law, which basically an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an unbalanced force. So inertia is basically the resistance of an object has to the change. If you're looking at the moment of inertia, there's basically 2 things in most dowel plate indexing applications. There's the dowel plate itself that needs to be calculated. There is the fixture and product weight at each of the stations that needs to be calculated. Now, many times in today's world, the sophisticated CAD systems that are used for solid modeling can calculate the inertia of all the products, and you'll have that value. It's typical that the values in metric terms are going to be in kilogram meter squared. In English standard units, you will actually have different terms of pound inches squared or inch pound seconds squared. And you also need to consider the inertia of anything that is moving from the indexer itself. So at the right top portion of this slide, you'll see that there is a dowel plate actually installed on a rotary indexer. Over to the left, you can see that the rotary dial plate itself. How do we look at this? Typically, it's going to be a hollow cylinder, okay? So if you look at the equation for inertia for a hollow cylinder, that's pretty much what you're going to use for calculating what would be the actual inertia of the dial plate that is going to be on top of the indexer. All right, so if you don't have it from your CAD system, you could go into some detail like I've shown here and actually calculate it. Now, this is just an example, and in this example, we're using the metric system, and we're looking at the actual density of the plate, kilogram meters cubed. You have pi, you have the thickness of the plate, which is h here, and you have the 2 radiuses. Now you have the ID and the OD, of course. Okay, so using the basic equations, you can see that the units are going to end up in kilogram meter squared for inertia of the actual dial plate. So that's just an example to show you what is typical whenever you're going through an application. The next part of this is actually going to be what we were talking about with the moment of inertia, which is basically the measure of the body's resistance to angular acceleration. It's equal to the product of the mass of the body and the square of its distance from the axis of rotation. You can think of that as the actual fixture and product weight at each of the stations. And here you can see mass times radius squared. You need to account for however many stations you actually have. And of course, this number can be significant because you're at a radius squared. So it's not something that should be taken lightly. You want to make sure that the calculations are done to include this. And you want to compare whatever indexer you're looking to use. And that's always going to be something that's published for the ratings of the output torque of the indexer. Now, when you get to that point, oftentimes people may consider, well, I can use a very small indexer and use a very large diameter plate and put wheels under it. Now, is that always the best situation? Maybe not, because you do need to consider friction. Now, with any system, when you have a bearing, like the cross roller bearing that we discussed earlier, you have to take into account the friction, which is the bearing drag. So that is additive to your output torque. But from this illustration, you can see that if you have rollers underneath of a dial plate, you're going to increase because you're going to have a torque due to friction, which is the coefficient of friction, basically times the weight and the radius of where the rollers are located. That number can add up in a hurry, and when you add that to the inertia torque, or torque due to acceleration, you actually could have a significant number, and you want to compare that to what the product is rated for. So just keep that in mind, that oftentimes you want your indexer product to be so robust that you do not need to add any type of rollers to the underneath of the dowel plate. Okay? Another consideration oftentimes is the power off or holding capabilities of the load. In a power off condition, there can be two distinct products used. In a lot of mechanical cam indexers, it's often common to have a ball detent torque limiter clutch at the output of the indexer where the dowel plate mounts to. And what happens is, if you have a situation where torque is exceeded, power off condition, a jam, the clutch will actually free itself from the detents and disengage from the power source. Now what that does though is the output inertia is freewheeling, and so you're still moving at the output. In this example, we actually have a brake, and another way to accomplish power off condition is to consider a backlash-free brake at the output. The brake will hold the load, and it will also prevent any type of freewheeling of the load. So in this illustration, you have a compact ring drive product that utilizes the option of an integral brake right into the center opening. And by doing this, it doesn't increase the overall package size. You still maintain a small hole through the output center as well, and therefore you can still use it for the plumbing that we talked about earlier. This is a nice feature because you are holding the load at the output itself. So something to consider whenever you're looking at your application. So hopefully that gives you some of the information that helps you make better decisions when you're going through and asking questions, looking at your design, making determinations. Just real quickly to go through the steps that I just outlined in an example. And in this example, I'm actually going to just use English standard units, the imperial system. No real reason why other than just to show you different ways. Certainly you can use metric system or English standard. And so here we were looking at average velocity earlier and basically get to the point where we have maximum velocity, which is 2 times average. And then in this example, we have maximum acceleration, which is taking the velocity and dividing it by 1/2 second for the time, and you're going to have 1.256 radians per second squared. So we've actually calculated what the acceleration is. Now it's an important element to find out the inertia. So we do have to take into account the inertia of the indexer that we are considering using. And this is actually at the output, which in our case is the gearing itself. And then we want to look at the load inertia. And again, this would be either calculated from your CAD system, or you would do the calculation based on some of the elements I outlined earlier. If we look at the total inertia, taking into account the additive PRD output inertia as well as the load inertia, then we will look at torque due to acceleration, which will be the acceleration times the actual inertia value. And that, in this case, gives you an output in inch-pounds, which is torque, 115.648 inch-pounds. Bearing drag, as I mentioned before, must be considered. So this would come via a catalog page, which would come from the product itself, and that is where the 354.03 inch-pounds comes from. Now what we do is we look at the total torque at the output, and we add the two numbers together. And once you get that, you can actually compare that final output torque number to what is in the catalog. Now, one of the nice features with the roller pinion system that I've been talking about is that you do get a reduction. And so in this case, you have 64 on the gear at the output, and the roller pinion has 10 rollers, so you get a 6.4-to-1 ratio. So keep that in mind, in that when you're looking at the maximum velocity again and the max acceleration, in this case, we will look at how fast the pinion is actually rotating and what the acceleration of the pinion is. And then we will take into account the inertia of the pinion. Now, inertia is always going to be divided by the square of the ratio when you're reflecting it back. So we're taking that inertia that we calculated earlier and we're reflecting it by the ratio of the 6.4 squared. And we're going to basically end up with our torque due to acceleration at the pinion, which again gets back to acceleration times the inertia. We will again take the friction torque into account. Now, torque is going to be divided by the ratio, but it is not the square of the ratio. When we add those numbers together in this example, we will end up with 120.433 inch-pounds of torque at the pinion. And from there, you have all of the items that you need for basically looking in the catalog to size both the pinion and gear as to the product itself. All right, so I appreciate it. Lisa, I'll hand it back to you.
Thank you, David. Thank you very much for that. Very, very cool. We have a few questions here, but just out of curiosity and to follow up on the last bit there, how much assistance would Nexen give to a machine builder to kind of go through some of the velocity and torque calculations? And are there any tools or any websites that you'd recommend our attendees visit to maybe get more information about, you know, Nexen's offerings and in supporting those kinds of engineering tasks?
Sure. I appreciate that, Lisa. Thank you. Nexen, of course, is located in Minnesota, and we pride ourselves on having a technical resource group that is available at any time. Certainly, these will be people that you can call, and you can talk to them, and they will walk through the design. They will actually go through a go-to meeting like we're doing today, if that is something that you would like to share resources back and forth. In addition, we do have on our website, nexengroup.com, an online chat resource that is available. And the website itself does give plenty of detailed information for solid model CAD drawings, also gives a lot of capabilities of every single product based on product number. And we also pride ourselves on the fact that we have local representation at all of the states, and we can assist on-site whenever necessary through either a representative or a regional manager.
Excellent. Nice. The first question we have here, and I think this one may garner some exchange after this webinar, but can I get a certificate of attendance at the conclusion of this webinar? We'll be in touch for that. We can offer something that is hopefully useful. Next question, David, maybe you'd like to answer this. What are some limitations of pre-engineered indexers?
Okay. So some of the limitations when you're looking at that would really have to do with the torque capacity versus the index displacement is the way I would look at that. There may not be flexibility for changing that depending on the design that you're using a pre-engineered indexer. And what we would want to basically look at is if it is pre-engineered, you want to have a very high capacity output bearing and the flexibility to change displacement and motion profile at any time for a given product number.
Okay, got it. Next question, this is again another housekeeping type question, but is it possible to share this presentation? Yes, indeed. To this attendee asking this question, we'll provide email follow-up with a link once this is loaded online. So thank you for that. Next question. This is a technical question. What are some things that positively and adversely affect rotary indexing performance in life?
Well, I would think from some of the parameters we outlined, proper selection up front based on the load criteria compared to the rated capacity of the unit that you're looking at, that's critical for the maximum performance. So certainly you have to go through all of the sizing steps that we outlined and compare it to the recommended unit and make sure it is actually the proper selection. That's going to go a long way to making sure that you have a positive unit. Stable machine frame is something that needs to be considered too. The machine frame is basically what you're securing the indexer to. You want to make sure that this is vibration free. The dowel plate that we talked about, the proper machining of the dowel plate and the proper fastening of the dowel plate to the output of the indexer. All of these things are certainly something that you want to look at. And we even touched on it earlier, but a large diameter thin dowel plate secured to a small indexer with wheels under it, that can certainly adversely affect the performance and the life of the unit. Accuracy can be adversely affected as well. And I would say also the axial and radial forces. Certainly, if you have an application with axial and radial force and it's exceeding the bearing capacity, then you're certainly going to have an adverse effect for performance. I think last, probably I would consider the environment. Environmental considerations are always something that you want to look at that could adversely affect performance. So keep that in mind as far as having something that can work well in the environment that you're looking for.
Excellent. Touching on bearings, we actually have another bearing question. What is done to protect the bearings from arcing when used in welding applications?
Actually, that specific application for welding, Lisa, I think that'd probably be a good subject that we could cover offline and go through that specifically. I think that in a lot of welding applications, it's very specific to the design itself. So we could certainly touch on that.
Okay, perfect. We have another request from a licensed PE there asking for a certificate of attendance. That seems to be request here. So we'll, again, I think that's another item for follow-up, and we'll be in touch. Next technical question, what size indexers do you offer?
You know, we offer indexers from very small, I would say, up to a very large range as far as capacity goes. And so let's just put it in perspective of general size to begin with. Nexon's product, for instance, it's pretty easy to understand. The compact ring drive, the model 250, CRD 250, the 250 stands for 250 millimeter diameter, and that is the bolt circle diameter essentially at the output. And we go all the way up to a PRD 1500 as far as a packaged product goes, and of course a 1500 would be 1500 millimeter bolt circle. And that 1500 millimeter diameter bolt circle, in that particular case, it has a peak output torque rating of 1,936 Newton meters. Has an accuracy of plus or minus 11 arc seconds and a repeatability of plus or minus 1.2 arc seconds. It's packaged up complete. And Nexon actually will explore custom units as well if we need to increase that load capacity with a larger pitch on the ring gear, maybe multiple pinions, a larger bearing. All of those things are considered whenever we're looking into some type of specific application that we can work with.
Excellent. Well, David, I think we've used our full hour and have run out of time. So this concludes our webinar. So another thanks to Nexon for being our sponsor on this. And thank you, David, for doing a deep dive on these indexers. Attendees, please note that the on-demand version of this webinar, minus my slide snafu, will be available online at the address you see here, designworldonline.com. And we thank you very much for your time. Have a good day.